All right, hello everyone. Sorry, my microphone was not set up correctly, but hello. So today we're going to be talking about recursion. So we're going to start with recursion and how that relates to divide and conquer strategies. Just some reminders. Quiz. What quiz are we up to? Quiz 5, I think? Or quiz 6? Either way, there's a quiz due tonight. Um, there is a quiz due tonight. There will be a quiz released tomorrow. Homework 3 is due tomorrow night. It is not particularly long. Homework 4 will be released tomorrow. Homework 4 covers recursion and concurrency. And coincidentally, today we're talking about recursion, and tomorrow we're talking about concurrency. So, good, works out quite well. From there, just some reminders. So next week, I just want to I'll outline the remaining portion of the course because there has been a slight change, which I'll get to in a second. Um, so that is the rest of this week. Tomorrow we cover concurrency. Next week, on Monday, we're talking about linked lists and TSP. On Tuesday, we're going to be discussing trees and heaps. On Wednesday, binary search trees. And then on Thursday, I'm actually going to do a couple topics that kind of got shuffled out. So we're not going to do Java streams and functional programming anymore. Instead, we're going to be doing abstraction with collections. We'll talk about what I mean by that. And then separately, we're going to talk about exceptions. And these were things that we would have covered earlier, but the class kind of got shifted around. And since neither of these are super relevant to the homework, I've kind of put them on the back burner. Friday of next week, for a rare, actually for the first time this term, Friday we will have class, but it will be final exam review. We'll talk about what that's going to look like really once we get into Thursday. The final exam for the class will be not obviously 2 days from now, Saturday, but a week from then. Homework 5. So homework 4, as I talked about, is on these topics. Homework 5 is specifically on linked list and TSP. I'm actually going to... Wow, my lighting looks... I swear I'm not holy. I don't... There we go, that fixed it. I don't know what happened there with the lighting. And heaps. Like, it didn't get brighter in my room. I just looked at my screen, and apparently I was like an angel at the end of a cheap 90s movie. Anyway. And then heaps will be the last part of homework 5. Homework 5 will be due Friday night of next week. Homework 4 will be due Tuesday night. So it is a bit of homework to do. I will say that there's not a lot of code with homework 4, but it is harder. Homework 6, I've intentionally tried to reduce the amount of coding required, but you will need to apply an understanding of what we call recursive data structures. But in order to talk about recursive data structures, we need to talk about recursion. But before I do, are there any questions about any of the announcements? So today, we're doing this. Tomorrow, we're doing this. Homework 4 will be on this. I guess in theory, I could release homework 4 today. I may release it early, but that's just so that way people who are done with homework 3 can get started on it. So will there ever be a homework? No, there will not be. So that is something that we do in the fall and spring. That is an assignment that has been pared back rather significantly, just because of it's always been the hardest assignment in the class. In the summer, it's just not realistic to do because it would take a day and a half to teach GUIs. So it's a day and a half I can't teach other concepts. And that then means that it's concepts that are more immediately important to 2150. So I had to take a pick. So homework. So there are 6 homeworks, but remember the first homework was homework 0. So 0, 1, 2, 3, 4, 5. So 6 homeworks, but we started with homework 0 because I thought I was being clever, and it turns out I'm actually just being confusing. So I'm probably not going to do that anymore. I was being clever because like, oh, it prepares you to think about arrays. By the way, no, I'm still bald. I felt like wearing a hat today. I don't really have a good reason. I had a bit of a headache. That's about it. All right. So, why are you wearing the headset? Good point. Fair point. All right. That actually, I don't have here was why I was wearing the headset. I just got out of an interview. We're interviewing faculty candidates, so that's why I was wearing the headset. Was it's better for one-on-one communication. There's less background noise that gets picked up. My cat was just sitting here meowing the whole time, so good point. All right. So with that, today we are going to be discussing recursion. And with most things, if you ever are unsure what recursion is, by the way, look, here are all the websites I like. Yeah. Now you get to see it. Let's see. It is Recursion is what I want to Google. Recursion. Well, let's see. Recursion. Did you mean recursion? Did you mean recursion? Did you mean recursion? Technically, this isn't really recursion. This is more of a joke. I suck at chess. I want to be very clear about that. I'm a sub 1200 rated chess player. So no, for the sake of my dignity, I will not play anyone in chess because all of you are probably better than me. I also like watching chess. I just suck at it. Anyway. So recursion is not infinite. Then that joke may imply that it is infinite. Recursion is not a infinite cycle necessarily, though it can be. Recursion rather is a self-referential process. So you can see, for example, the fraction of this image, which is white, the fraction which is black. This is all self-referential. And when we talk about recursion, we are talking about solving a problem by applying a small modification to a solution of a simpler problem. That is, take a problem and your solution is solve a slightly simpler problem and then apply some change to that solution. We'll get into some practical examples of what we mean by that in a second. So a recursive definition is one that contains itself in its own definition. So a noun phrase is a noun, and it's also an adjective followed by a noun phrase. So you don't have an infinite loop here because you have kind of like an off-ramp on the highway noun. This is an example. So I can take a noun like I could take something like man, and then I could add an adjective to the front. Balding man. This is now a noun phrase. From there, we could do a sarcastic balding man. So this is an adjective followed by a noun phrase. And this is a noun phrase because it's an adjective followed by a noun phrase. And this is a noun phrase because it's a noun. And self-deprecating. Another one. I'm just pretty much describing myself, as you can tell. The point is, this is the definition of a noun phrase. It's an adjective followed by a noun phrase, which is an adjective followed by a noun phrase, which is an adjective followed by a noun phrase, which is a noun. So it is just a self-referencing process. That's what we mean. And this shows up not just in terms of algorithms, but also in terms of data structures. And we're going to look at these next week. But today, oh, by the way, I got my stream deck all set up. I'm actually pretty happy with it. So, like, I can change scenes. So if I want to go to the whiteboard, and webcam, and if I want to say the stream's over. Anyway, I thought that was really cool. I had a lot of fun setting that up. Because now I don't have to remember hotkeys, which is what I had to do before, which is why I kept having so many erroneous scene switches. So, that's fun. Anyway, so, when we're thinking about recursion, what we want to do is we want to think about how do we take a given problem and reduce it to a smaller version of itself. How do you make a given problem smaller? And at base of that, there has to be some version of the problem that is so small that it is practically axiomatic. An axiom is something like 1 equals 1. Try to prove to me that 1 equals 1. It's philosophically kind of troublesome, right? But we accept as a reality that 1 equals 1, and then we can build from that axiom more complex assumptions. So the idea of a base case is this is such a simple version of the problem that the solution is self-evident, that you can't escape it. And the question is, how do we take this complex problem and reduce it towards that simplest version, that base axiom, and then we build it back up to the large problem? That's the idea. It's more of a top-down solution. Whereas with some looping we've done, it's mostly been bottom-up. So for instance, there's recursive definitions. There is n factorial, because n times n minus 1 factorial. There are non-mathematical ones, but this is straightforward. There's a recursive procedure, a process that calls itself. We can have recursive data structures. This node class is the basis of the linked list. And we will be talking about linked list next week. And your homework 5 will be on linked list. So, thinking of a recursive mindset. We talked about, for example, how to do this type of search as a binary search. Now, we implemented that with a while loop. But the idea, actually, is inherently recursive. Now, we wrote it with a loop, but recursion doesn't actually require code recursion. And that may sound weird. We're going to talk about how to do recursion in code, but the idea of a recursive mindset is separate from that. And with a recursive mindset, what our emphasis is on taking a complicated problem and finding ways to make it simpler. So, we could, instead of writing it recursively, we could define, and this is pseudocode, this is not formal Java, we could find page number from a given book by first flipping to the middle of the book and looking at the current page we are on. If the page is the page number we're looking for, we're done. So this is kind of a starting, this is, we've hit the jackpot, we found the page, we're done. Otherwise, if the page number that we're looking for is before the current page we're on, we're only going to recurse on the first half of the book. We're still looking for the same page number, but we're only going to look in the first half. We're going to completely ignore the second half. Otherwise, if the page number is after the page, we're going to find the page number in the second half of the book. So this is the same idea, but now I'm not expressing it with a loop. Rather, I'm expressing it as a self-referencing process. Because the way that I'm going to find the page number in the first half of the book is procedurally no different than the way I'm going to find a page in the book at all. Another example is Towers of Hanoi. This is a classic game, and the goal is you start with 3 pegs. You start with all the elements on the left, and you're going to move all of the elements to the right. But there are rules. We live in a society. We're not animals. We have to follow the rules. And the rules are, you can only move 1 disk at a time, and you cannot set a larger disc on top of a smaller disc. So let's play Towers of Hanoi. Now I'm going to define this problem first as in this way. I'm gonna make a way to list my moves. So first, I'm going to start, just as an example, moving disc 1 being the smallest disc. I'm going to move disc 1 to the right. That is a right move. I can also move disc 1 to the left. That is a left move. So that's straightforward. But I'm going to cheat a little bit. I'm going to say that these 3 pegs form a circle. By that I mean, I can move disc 2 to the left, and it goes off the left side of the screen and comes back to the right side. Just to show that again, if I move disc 2 to the right, it comes back over to the left. So left, wraps around, comes over here. So based on that definition, there's actually a very simple solution to any given Towers of Hanoi. If I want to move these pegs to the left, because effectively I'm taking the pegs that are on the left peg and moving them to the left to the right. If I want to move n pegs to the left, the solution broadly is, first, I need to get n minus 1 pegs, that is every peg but the last one, onto the middle. That is, I need to move them to the right. So that's the first step, going from here to here. Now that step has many sub-steps, but the starting point is I'm defining this problem by going from here to here. Move n minus 1 disc to the right. I then move the nth disc to the left, so it wraps around, ends up over here, and then once again I move n minus 1 disc to the right. So to summarize those steps, by the way, this is my autobiography. I'm done. To summarize these steps, to move n discs to the left, move n minus 1 discs to the right, move the nth disc to the left, move n minus 1 discs to the right. So if this were my algorithm, well, I do need to take a couple other steps. First, I need to also not just be able to move to the right, or left, I also need to be able to move to the right, so I'm going to add move to the left, right, then move n minus 1 disc to the right, left. Technically, Will's already a nickname. Anyway, right, and then left. So if I'm moving n disc to the left, I go right, left, right. If I'm moving n disc to the right, I go left, right, left. But there's some point I have to stop. So here's a question. What is the easiest version of Towers of Hanoi to play? What would be the easiest version? I'm going to head over to the whiteboard here. But how many discs would Towers of Hanoi need to be as easy as possible? 2? All right, well, let's think about that. So I have 3 pegs. Here are my 3 pegs. And if I have 2, well, that still takes a bit of work. Because with 2, I'm going to have to move the small peg here, and then the larger peg, or larger disc there, and then the small peg on top of it. That takes 3 moves. Man, 3 moves is a lot of work. It's a lot of work. I don't know if I want to do that much work. What's an even simpler version? 1? And, well, if I have 1 ring, that's a lot of work. I got to move that whole ring. How about 0? Now this is my kind of work. All right, ready? I'm going to move 0 pegs. Are you ready? Here we go. Watch closely. I'm going to move 0 pegs and... All right, I'm done. All right, I know some of you missed that, so let's just do a quick little redo. I'm going to move 0 discs again. All right, ready? Okay, all right, we're good. Everyone got that, right? There it is. That's the easiest version of Towers of Hanoi to solve. I'm done. I have won the game. There are 0 discs. So, the simplest version is actually 0. 0 discs. Because I don't need to do anything. I'm done. So, if n is greater than 0, I'm going to do these 3 steps. Else, I'm going to do nothing. I'm just going to return. I'm done. It turns out that from this solution, I can very easily write a program to give me the steps to solve Towers of Hanoi. So let's try that. Let's say I wanted to play Towers of Hanoi with 5 discs. And I don't want to make any mistakes, so I write a program to help me. This program, which is already uploaded on the class notes today, this program will tell me how. If n equals 0, I return. Otherwise, in order to move n discs, either left or right, true equals left, false equals right. It's a Boolean. If I'm moving n discs, how do I do it? First, I move n minus 1 discs in the opposite direction. So if left is true, this moves to the right. If right is true, this moves to the left. Then I print move disk number n to the left or right, depending on which direction is true. If left is true, I go left. If left is false, I go right. And then I remove n minus 1 discs in the opposite direction again. This is working code. And if I run this program, I'm going to run it. I'm going to just say n equals 5 for now. If n equals 5 and I run the program, here it gives me a list of steps. Let's go ahead and let's copy them. Put them into Notepad. And let's follow these steps. Actually, there's a lot of them. All right, here we go. So move disk 1 to the left. Move disk 2 to the right. Move disk 1 to the left. Move disk 3 to the left. Move disk 1 to the left. Move disk 2 to the right. Move disk 1 to the left. Move disk 4 to the right. Disk 1 left. Disk 2 right, disk 1 left, disk 3 left, disk 1 left, disk 2 right, disk 1 left. And now we are here. Sorry, we're here. We now move disk 5 to the left. And then notice that these steps match exactly these steps. They are a complete match. That is not an accident. So, disk 1 to the left, 2 to the right, 1 to the left, 3 to the left, 1 to the left, 2 to the right, 1 to the left, 4 to the right, 1 to the left, 2 to the right, 1 to the left, 3 to the left, 1 to the left, 2 to the right, and 1 to the left. I followed these steps exactly, and I won. And I came up with the code that generates this in this many lines of code. That's all. That's the entirety of what I need. Now, could this be done with loops? Yeah. But in my opinion, it would be substantially harder. It would be substantially harder. And that's a point here. Everything we do with recursion, we can, in theory, do with loops. But the algorithm might be easier to write recursively. Because you can think of the problem not as a whole, but as a series of interacting small problems. So I don't think about how to move all 5 disks. I only think about how to move the 5th disk and let the 4 disks below it handle themselves. Any questions about how this code works or why it works? Of course, the key emphasis I want to place is what function is being called here on line 11 and on line 17. Well, it's the function calling itself. That's the key. It's the function calling itself. And you can have this. That is, in fact, the nature of recursion. And we're going to trace how this recursion works with some simpler examples. I apologize if you can hear my cat meowing. He is being very bad. He's climbing on top of stuff trying to get my attention. Anyway, any other questions on this code before we move on? Or on Towers of Hanoi? Now, there is a legend. There is a legend which says that there is a legend that says that somewhere on a mountaintop, because they're always on a mountaintop, there are a group of monks. How do you come up with this solution? Again, I start by defining the problem this way, and then I write code to match this solution. Because that is the solution to Towers of Hanoi. That's how you have to play. It doesn't matter how many discs you have. This is the pattern you ultimately have to follow. Give me 1 second. I apologize. All right, apologies for that. I am back with that. This is the general solution. It doesn't matter how many discs you have. Now, there's in theory a group of monks, and that group of monks is playing Towers of Hanoi with 64 discs. Because it's always monks on a mountaintop doing something. And these discs, by the way, are made of diamond. Or excuse me, gold. The discs are made of gold. The pegs are made of diamonds. Because of course they are. And the myth is that when the world comes to an end, or excuse me, when they finish playing, I should say. I got the ending before. When they finish playing this game, then the world will end. And the way they play is they move 1 disc every second. And again, they're playing with 64 discs. And they work they work with shifts through the night. They've been at this for years. So the question is, how long until the world ends? Now you may be thinking 2020, maybe this is the year, you know? The question on my mind at least is, will we get Winds of Winter? That is the question. Will we get Winds of Winter? George R. R. Martin says he's made progress. Will we ever see it? Well, in order to figure that out, let's take a minute and let's work out how many moves each version of Towers of Hanoi takes. And doing that, we can say, okay, clearly 0 moves takes 0 seconds. And if we have 1 disc, all we have to do is move the disc from left to right, so that's only 1 second. If we have 2 discs, you have to first move the small disc to the middle, then move the big disc to the right, and then the small disc to the right. That takes 3 moves, 3 seconds, 2. From there, using our own recursive definition, remember, to move 3 discs, I first have to move 2 discs one direction, so that takes 3 steps. I have to move the 3rd disc, plus 1, and then I have to move these discs again, these 2 discs again, plus 3. So this is 7. For 4, move 3 discs to the one direction, plus 1 to move the 4th disc, plus 7, 15. And if you look at this pattern, you'll notice that there's actually a mathematical identity for this. And that is the number of moves it takes to move n disks equals 2 to the power of n minus 1. So if I have to move 5 disks, it's going to take 31 moves. If I have to move 6 disks, it's going to take 63 moves. So the question is, how much time does 2 to the power of 64 minus 1 give us? Let's find out. He did also say that 5 years ago. You're exactly right. Trust me, I am jaded AF on this. I read Game of Thrones when I was in high school. Okay? I'm old now. Just enunciating that point. Anyway, to that end, let's trust the good old Google calculator. And what is 2 to the power of 64 minus 1? All right, well, this is a pretty big number, but that's in seconds. So how many minutes is that? Divide by 60. How many hours is that? Divide by 60. How many days is that? Divide by 20 or 4. That's this many days. How many years is that? Divide by 365.24. So that is this many years. So the good news is, and this is, let's see, that's thousands, millions. So it is 584 billion. So the good news is we will eventually get Winds of Winter. Dream of Spring, it's a lost cause. He'll never finish it in time. But Winds of Winter, we will get. Dream of Spring is the planned 7th book in the series, and I have fully accepted that the best case scenario is someone else finishes the work. And he's emphasized that he won't allow that. So just expect we're never going to see this, and we will be stuck with Game of Thrones Season 8 forever. Mortality is a terrible thing. Anyway. All right. Back to not ranting about Game of Thrones and instead ranting about recursion. The point is, that's how many moves it takes, and that growth rate is exponential. That function on the board is an exponential function. And it turns out that there is no more efficient solution. That is the most efficient. So Towers of Hanoi is one of those things that we've talked about where there isn't anything better than an exponential solution. One cannot be created. And that's often where recursion will be used. But let's do a simpler version of recursion. Let's take a recursive function, specifically factorial. And factorial, if you're not familiar, is the mathematical function n factorial that is equal to n times n minus 1 times ... times 1. It is this series. Now, factorial is not just some hypothetical mathematical curiosity. Factorial has a very, very specific purpose, a very specific thing. For example, I have 4 items. I have a green marker, a blue marker, an eraser, and a TV remote. How many ways can I arrange these things? The number of ways I can arrange them is I can pick any one of these elements to be the first item. That's 4 possibilities. Times, at that point I only have 3 left. So pick any one of these 3 items. So times 3. Pick any one of these 2. Times 2, only 1 left, times 1. 4 times 3 times 2 times 1. So factorial is not just some curiosity. It has a very, very technical purpose. It is the number of ways to arrange n things. And this series grows mind-bogglingly fast. You cannot believe how fast this series grows. It is worse than exponential. The human brain is just not conditioned to deal with factorials at any scale. But we can define this recursively. For example, let's say that first I'm going to say, and this is a bit weird, 0 factorial equals 1. And that may seem strange, but I have 0 things here, and I can arrange them one way. Here it is. So that's why 0 factorial is 1. 1 factorial can then be defined as 1, because there's one way to arrange one thing. 2 factorial equals 2 times 1. I'm actually going to write this in a different way. I'm going to write it as 2 times 1 and 1. Then 3 factorial equals 3 times 2 times 1. 4 factorial equals 4 times 3 times 2 times 1. 5 factorial equals 5 times 4 times 3 times 2 times 1. And the reason I wrote it this way is writing it this way is going to help me work out my recursive definition. For example, notice that 5 factorial contains all of the elements in 4 factorial. And 4 factorial contains all of the elements in 3 factorial. This is the basis of how I'm going to define my recursive function. So here's how we're going to do it. Based on what I drew on the whiteboard, I can say that n factorial equals n times n minus 1 factorial. And this is a recursive definition. If instead of the symbol exclamation point, I define it as a function, I can then say factorial n equals n times factorial n minus 1. But I have to have a stopping point, because I can't say factorial 0 equals factorial negative 1. How do I arrange negative 1 items? I don't know how to do that. So I'm going to say as a base truth, factorial 0 equals 1. This is my axiom. This is my base case. And using that, I can then write this function as follows. First, public static int factorial int n. If n equals 0, this is my base case, or my axiom, as I'm referring to it as. You will typically see this term. Actually, you almost exclusively see this term on quizzes and exams. I'm just emphasizing that this is an axiomatic truth. That's how I define my base case. If n equals 0, return 1. That is, and I have the wrong equal sign, but otherwise, that is my base case. Else, and I don't necessarily need the word else here. It's fine if you have it. I'm going to write it here just to make the code easier to read. Else, return n times factorial n minus 1. What function is this calling? It's calling itself. And if I test this, public static void main string args system.out.println factorial 5 should give me 120. Because 1 times 2 is 2, times 3 is 6, times 4 is 24, times 5 is 120. And there you go. I get the correct answer. Now, I do want to illustrate, though, what actually is happening here. First, I'm going to print here, system.out.println, I have entered factorial with n equal plus n. I'm printing that statement at the beginning, and then anytime I return, right before I return, I'm going to print system.out.println, I am returning 1, and I am returning plus n times, well, here, let me do it this way, actually. Int f equals factorial n minus 1. And then I'm returning n times f. Why is it not like this? Oh, there we go. Okay, so this is, I'm intentionally just printing right before I return. And the reason I'm doing this, I want to see you to see the order that these things happen in. Hang on. Oh, sorry, forgot a semicolon. Notice that it says I have entered factorial 5, then 4, then 3, 2, 1, 0, and then I am returning 1, 2, 6, 24, 120. The idea is I first decompose down to the smallest problem and then build back up to the largest problem. Exactly, Watch 77. This is like a stack. And it's like a stack because of how the calling stacks work. So let's go back to the whiteboard and let's illustrate this factorial code. And I'm going to see if I can blow this up a bit. I do want you to be able to see the code and what happens here as I illustrate this. So with the stack, and I'm only illustrating the stack here. Yes, there is a heap, but we don't need it. So I'm just illustrating the stack here. We don't care about the heap for the time being. At the base of my stack is main. That hasn't changed. This is main. And if you look in the code for main, I simply call factorial 5. So I'm trying to print factorial 5, but that means I need to pause on line 16. And I pause on line 16 and call factorial 5. So that gets placed on top. And this is factorial. And it has a local variable called n equal to 5. From there, I enter this function at line 4. I print. So I'm going to write, this is just my console. This is what I'm printing. I'm going to print 5. I'm not going to write out the whole sentence. Just write the value of n, 5 here. Because that is the value of n. I'm then going to ask, is n equal to 0? It is not. That is at line 5. At line 6, sorry, I don't go to line 6, forgive me. At line 5, n is not equal to 0, so I proceed to the else statement at line 8. At line 8, I then say f equals factorial n minus 1. So what does f equal? Well, I don't know yet. I have to figure out what factorial n minus 1 is first. So I need to call factorial with n equal to 4. And now this is paused at line 9. And I need to execute factorial n equals 4 first. Turns out I'll get to the same line 9. I'll say f equals, and I won't have an answer yet. So I'm paused at line 9. I need to call factorial with n equal to 3. I then reach line 9, f equals, I don't know yet, 9. That makes me, and I have to be a bit smaller here, factorial n equal 2. F equal, I don't know yet, I need to solve that. Just because I'm out of space, assume that this is above this. Then I call factorial n equal to 1. I get to line 9. I still don't know what f is. So then I call factorial n equals 0. And at this point, something different happens. Specifically, at line 5, because n is equal to 0, I hit the return statement. By the way, I haven't been printing, but every time I call this, this does print 5, then 4, then 3, then 2, then 1, and then 0. That's the print statement at line 4. From there, this is at line 7. It hits return 1. It also says I'm returning 0. So I'm just going to write R0 for returning 0. It returns 0 to line 9. So then we take that 0 value, or excuse me, not 0. It doesn't return 0, it returns 1. Forgive me. Then we take that 1 value, we pop the top function off the stack, sending that 1 value to the next highest function on the stack. Specifically, factorial where n equals 1 at line 9. So that is here. And we say f equals that return value. So f equals 1. I then print I am returning n times f. So that is 1 times 1, 1. And because I then say return that product, return 1, that gets returned to the next highest element on the stack. And I pop that function off. Then go to line 9, plug in 1 for factorial n minus 1 here. F is 1. I return 2 times 1, so I return 2. And because I'm returning, pop that off the stack. That means f equals 2, because it equals that return value. Then we return 3 times 2, so we return 6. Pop it off the stack. F equals 6. We return n times f, 24. So we return 24. Pop that function off the stack. F equals 24. 5 times 24 is 120. We return that. And then finally 120 goes to main, where we were at line 16. And at line 16, we print 120. So every way that we've illustrated tracing function calls before with the stack, that applies to recursion. It hasn't changed. It's just that now you're getting the same function on the stack multiple times. Are there any questions about that? Any questions about that illustration? Let me do that. Let me see if I can find a better place to put this so it's in my field of vision. I don't have to turn my head to look at my stream deck. That kind of works. Oh, sorry. There we go. All right. So that is the stack. And we tried to illustrate it here, but I wanted to do that step-by-step illustration so you see how it works. So again, whenever you're defining a recursive function, we define the base case and the recursive step. So for example, we can implement it this way. And then from there, here is how we build the solution, the return values. So the idea is it uses the runtime stack in order to build that. We illustrated the runtime stack. You can see that illustration here going slide by slide. This is the same thing. And from there, we can do other simple mathematical functions with recursion. For example, now granted, Java does not do recursion this way, but we think of multiplication as the following. If I say 6 times 4, what I actually mean is 6 plus 6 plus 6 plus 6. I could then use that to say 6 times 4 equals 6 plus 6 times 4 minus 1, or 6 times 3, because I have 3 6s and 1. So let's write this multiplication function with recursion. Public static int multiplication int A, int B. In this case, given this problem, how I defined it, what is my base case? What factors of A and B tell me I have reached my base case? Or should I say A or B? Anyone? What would be my base case based on this definition I'm using? Because effectively what I'm saying is A times B equals A times, or A plus A times B minus 1. When would I stop recursing like this? Six times 0. Or I would stop recursing when B equals 0. What is my product? It's 0. So, if B equals 0, return 0. Else, sorry, I forgot the equal sign, double equal sign again. Else, return A plus A times, or actually, let me do it this way. A plus multiplication A B minus 1. This is how I can do multiplication. Now, I did see someone suggest 1. Sometimes the base case is 1, sometimes it's 0. In this case, I would argue 0. That's how I would think of it. So, let's just test this. System.out.println multiplication 6, 4. Let's make sure this works. Should print 24, and it does print 24. So I'm reasonably sure this is correct. Now from there, let's consider, could you have done this with loops like this? Absolutely. You could absolutely do this loop solution on the right. In this case, it's fairly trivial. In terms of converting from the recursion to the loop. That's not always the case. For example, I would be impressed if any of you could convert this into a loop. If any of you are able to do that, certainly let me know. Send me that code. I'd be very interested in seeing it. This is much harder to convert to a loop. Mathematically speaking, it must be doable, but it would be a lot harder to write that code. In factorial, it's trivial. In factorial, this is the recursion, this is the loop. But generally with recursion, we build the solution top down, and then from the bottom build up, whereas with iteration, we can just start at the bottom and work our way up. So, some languages don't support recursion. COBOL, which is still a very big language. COBOL is actually still extremely widely used by banks. Fortran is used in some legacy software. Lisp is a fun one. Lisp, Prolog, and Scheme, these languages almost explicitly use recursion. So here is a broken factorial function. And my question to you is, why is this function broken? What is wrong here? Why is this broken? The less than or equal to is not a problem. That's fine. But the other two answers, because the recursive statement is on the first line. That is the problem. Because we cannot recurse we cannot recurse before we check the base case. There is a base case, here it is, but because we recurse before we check the base case, this is going to lead to what in theory... that's fine, I should say. This part is fine. That's okay. The problem is, this line cannot be here. If this line were instead here, everything would be fine. This would be okay. But because the line is before we check the base case, remember, the base case is where we want to stop recursing. But if we recurse before we check whether or not to stop recursing, that means that we're going to get broken factorial 2, then 1, then 0, then -1, then -2. I used to live in Philadelphia, and if a train was full, sometimes you would just see it blow through the station, which was annoying because there were people who wanted to get off. But if this, like, it would just happen. This is what it's like. The station that you need to get off is broken factorial 0. The train just goes right through. It doesn't stop. And so, this is like an infinite loop, but there's a difference. Because, see, unlike in a loop, we're not building up additional memory. If we have an infinite loop, it's just going to cycle forever. The problem is, as we drew on the whiteboard with those stacks, every single function call in Java adds a memory cost. Every one of those functions on the stack costs some amount of memory. And no matter how good your memory is, your computer's memory is finite. And so if I make that change, this actually won't loop forever. Instead, what will happen... So I'm going to make that change here. Instead, what will happen is my program will crash with a very specific type of error. And that is... Hang on, let's scroll. I'm still scrolling. Here. Stack overflow error. A stack overflow error is caused when that stack that you're using runs out of memory. So you won't actually ever have to worry about an infinite loop with recursion because each function eats up more memory and eventually you run out. But that is what a stack overflow is. It's when, and this is, by the way, this is a stack trace. It basically pops everything off the stack and tells me what line of code we're at. I crashed here, which was called by this function here, which was called by this function here. All the way down, it's all line 4. It is all this line causing the crash. So that is what a stack overflow is. Are there any questions? All right, the last example we're going to do before we take our break and then move on to divide and conquer is the Fibonacci series. Have you guys ever heard the joke about the Fibonacci sequence? Has anyone ever heard that joke? Anyone? If you haven't, it's as good as the last jokes you heard put together, I swear. Thank you. Anyway. So the Fibonacci sequence, which comes from a priest watching rabbit populations. And when there were no predators, he found a sequence where each rabbit pair produced each rabbit pair produced a pair to replace themselves, but they produced multiple pairs, and anyway, it's a long story. But the purpose, there wasn't a lot to do back then. They didn't have Netflix. Lord of the Rings hadn't been written yet. There wasn't a lot to do. That is the Fibonacci sequence. So the Fibonacci sequence is first 0 and then 1. And then it is the sum of the previous two numbers. So 0 plus 1 is 1. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 8, 11, not 11, 13, I'm bad at math, 21, 34, etc. By the way, this series is exponential. It grows exponentially. It's a rather small base, but it is an exponential series. Forgive me, but that I can't have. Please don't do that again, because if I allow that in this chat, that is actually going to get me in trouble. That's not okay. Let's not do that. Thank you. So with that, we can program this by defining the Fibonacci as simply Fibonacci of n equals Fibonacci of n minus 1 plus Fibonacci of n minus 2. And then from there, we can then specify two base cases. Fibonacci of 1, this is the 0th number, this is the first number, so Fibonacci of 1 equals 1, and Fibonacci 0 equals 0. And we can define Fibonacci in this way pretty simply in code. Public static int fib, and it's going to be int n. If n equals 0, this is my first base case, return 0. Else, what is the big O complexity of recursion? So, it depends. And we're actually going to run into that here in just a second. So factorial is linear because this function gets called n numbers of times. Towers of Hanoi is exponential, but that's because the problem is exponential. Basically, when recursion creates branching paths, it's exponential. We're okay with that with Towers of Hanoi because there's no way to solve this problem that isn't exponential, because the best solutions of Towers of Hanoi require an exponential number of moves. We're going to run into a problem here in a second with that big O complexity that we're going to talk about. Else if n equals 1, return 1, else return fib n minus 1 plus fib n minus 2. This is a correct implementation, and we can test this. System.out.println fib. Let's take a look at the series I've written so far. This is 1, 2, 3, 4, 5, 6, 7, 8. Let's try fib 8, and if we get 21, I'm happy, and if we don't get 21, I'm sad. And then we have to debug. So we're expecting 21. Let's try that. Oops, I forgot I still have this in here. Let me fix that real quick. And there we go. I get 21. So I'm happy. Now, this function can be written with a loop. And this loop is going to look ugly. Public static int. I'm going to call this fib iter. That is using iteration or using a for loop. Int n. Now, first, I'm going to keep the same starting point here, and that's just to make it easy for me in a second. I'm then going to say that int previous equals 1, and int previous, that is the thing before previous, is 0. And then, while n is less than, while n is greater than 1, I'm going to say, first, int temp equals previous plus previous. That is the sum. I'm then going to say previous equals previous, and then previous equals temp. And then finally at the end, return previous plus previous. And if I did this right, I should get exactly the same solution. And if you're looking at this thinking, what is this code? That's kind of the point. The point is, it's harder to write this with a loop. But let's try. Oh, hang on. I forgot to do the most important part, n minus minus. Very, very important I do n minus minus. As you can see, I have an infinite loop now, but I fixed it. Okay, I was off by 1. How was I? Yeah, I was off by 1. So actually, I just want to return previous. I don't want to add previous. See, it's harder to write this. But there we go. This iterative Fibonacci now works. So let's test this. Let's make sure that we're getting the same value for larger numbers. The first thing I'll note is Fibonacci can grow quickly. So let's try Fibonacci of 25 and Fibonacci of 25. We'll do the iterative one first and then the recursive one second. All right, they're both giving me the same value. That's good. Now let's try 50. Uh-oh, we're getting negative numbers. How are we getting that? Well, the reason we're getting negative numbers, as I talked about before, and I'll terminate this for a second, as I've talked about before, integers have a maximum value, and Fibonacci, because it's exponential, exceeds that fairly quickly. So I need a larger output than an int. I actually need a long, which means I need to turn these values into longs. So I'm going to do this both for Fibonacci iterative and that. I'm going to make these longs. That way I can get a larger number. So now let's try 50 again. Oops. Hang on. That also needs to be a long. My bad. So now let's try this again. Okay, I get this number for 50, but why am I only showing one number? Why am I not getting Fibonacci 50? Why is this happening? Well, my program is still running. Huh. Let's try a smaller number. Let's stop this and let's try, I don't know, maybe just 40. Watch very closely the bottom of the screen. I'll run it again. Notice that there is a little bit of a pause here before that number showed up. If I change this to 43, notice that was a significant pause. If I change this to 44, it's an even longer pause. The problem with this solution is that this solution has an exponential runtime. This solution finishes so quickly, almost instantaneously, because this is linear. It's not because my memory is filling up. Memory is not the problem. Here's the problem. When I call an iterative Fibonacci, what is happening is I decompose 4 to 2 and 3. And then I decompose 2 to 0 and 1. Then I compose 3 to 1 and 2. Oh wait, now I have 2 2s. And I have 3 1s. What is going on here? Well, it turns out, let's now think of it in this way. Let's do Fibonacci of 6. Let's do Fibonacci of 6. And I'm going to break Fibonacci of 6 down into Fib 4 and Fib 5. Well, Fib 4 is broken down into Fib 2 and Fib 3. Fib 2 breaks down into Fib 0 and Fib 1. Fib 3 breaks down into Fib 2 and Fib 1. Fib 2 breaks down into Fib... Sorry, for consistency, I'm actually going to make this 1, 0 instead of 0, 1. Breaks down into Fib 1 and Fib 0. Now, this is only half. I still have to do this entire half. So this breaks down into Fib 4 times, or not times, plus Fib 3. And oh, look at that. I am going to have to put this entire tree over here as well. Now, I'm not going to write it for the sake of time, But this whole tree now has to be evaluated twice. This section has to be evaluated both here and there. Similarly, fib 3, I have to evaluate this part again. And it turns out that this means that I'm evaluating fib 3. 1, 2, and then one more for fib 4 3 times. And that means I'm evaluating fib 2 1, 2, 3, 4, 5 times. And that means I'm evaluating fib 1 8 times. And if you add that up, it turns out that the number of times I evaluate each, I evaluate fib 6 once, fib 5 once, fib 4 twice, fib 3 3 times, fib 2 5 times, fib 8, or fib 1 8 times. Hey, has anyone seen this series before? Has anyone ever heard of this series? That ring any bells? It's the Fibonacci series. And so, the number of steps that I need to do, the number of times I need to call Fibonacci is the Fibonacci number. So if I want to call fib 44, I'm going to recursively call fib 44 701,408,733 times. And as I said before, Fibonacci is exponential. So this is exponential. The linear version, however, here's the question. How many times do I loop? Well, I loop. This is n minus minus. I loop n times. I technically loop less than n times, but it's proportional to n. So this function is big O n, and this function is big O, and it's exponential, which typically you would write as 2 to the n. Technically, this is phi to the n. There's a number called phi. It's the golden ratio, and that's what it is, but this is still exponential. And that's why doing the naive recursion approach for Fibonacci is actually bad. Sometimes when you do a recursive solution, you can take a problem that is something like big O of n and turn it into exponential. So you have to always be careful not to do that. So with that, we're going to take our break. It's 2:15. I'm going to do a I don't know if I have time for a full 10-minute break. Let's call it 8 minutes, so we'll be back at 2:23. However, you can start on today's daily activity. You can go ahead and start on today's daily activity, as the daily activity only relies on things we covered in the first half of class. Just as a quick tip, you will need to use the string car at function if you've not seen this function before. Just to clarify what it does, string s equals bandana s.car at 0 would return the character capital B. S.car at 0 or at 3 would return lowercase d. It is the character at that index. So go ahead, you can jump into Discord with each other during the break and get a head start on the daily activity. And I'll come back here in let's call it 9 minutes at 24 past, and then we will do that. Do they have C strings in Java? You mean strings like in C? So they don't, because Java doesn't have pointers the same way C has. Strings in Java are null terminating. They do have a null character like C strings, but in C, you just use a pointer to keep track of the start of the string. You don't actually have strings. You just have character references. Java doesn't have pointer variables like that. Anyway, we'll be back at 24 past, but go ahead, jump in Discord, get started on the daily activity. All right, see you in a second. All right, welcome back, everyone. I frankly love the music in Civilization 6. As you can tell, it's the same song, but each era, as it progresses to the future, it builds more instruments, themes, more complex music. I quite find that fantastic. Anyway, now on to Divide and Conquer. So we have, of course, been talking about recursion. And we have talked about merge sort at a high level, that we're going to get into the nitty gritty here in a second. We've also talked about a binary search. And even when a binary search is implemented as a loop, the idea of the search, the motivating idea, is recursive. Take the bigger problem, break it down into a smaller problem. And we can do that as well with sorting. So here's how we're going to justify this. Last time, yesterday, we talked about how the selection sort was quadratic time. And to that end, I gave an example where if I took an array of size 8, whatever the contents are, I don't care. If I wanted to perform a selection sort, the number of steps was I had to find the minimum. I had to do 7 comparisons, plus 6 comparisons, plus 5 comparisons, plus 4, plus 3, and so on. That is the sum of every number from 1 to 7. Not counting my swaps, just counting the comparisons. So 1, ... plus 7. That is equal to 1 plus 7 is 8, 2 plus 6 is 8, 3 plus 5 is 8, plus 4. That is equal to 28 steps. Now, let's make that a little bit bigger. Let's say instead of size 8, this were size 16. Size 16. Now, that would mean that the number of things that I have to do a selection sort is 15 plus 14 plus ... plus 1. 15 plus 14, or 15 plus, 14 plus 1, so I can add a plus 0 here to make it easy. 15 plus 0 is 15. 14 plus 1 is 15, all the way to 8 plus 7 is 15. So that is going to be 15 times 8. 15 times 8 equals, doing some mental math here, 120. Take 120 steps. Someone please check my math, make sure I'm not wrong on that. But I'm pretty sure I'm right. 120 steps. So this would be if I did a selection sort. I'd have to do 120 comparisons. Selection sort. From there, let's consider the following. What if instead of sorting 16, I go and get a friend? And I get a friend, and what we're going to do is we're just going to break this in half. I'm going to sort the left half, they're going to sort the right half. So let's say the numbers were something like 20, 8, 14, 7, 6, 10, 2, 1. I don't want duplicates for now, though duplicates aren't a problem. I'm just trying to demonstrate something. Let's do 3, 4, 5, 13, 16, and 19. Let's say I got a friend, we broke this in half. Now, if I performed a selection sort here, this would take 7 plus 6 plus 5 plus 3 plus 2 plus 1 steps. That'd be 21 plus 7, 28. So a selection sort only on this takes 28 steps. But the key is I have to do it twice, right? So now I've done, add these together, I've done 56 steps. But if I do this, I only end up with 1 or 2 sorted arrays. I don't end up with 1 sorted array. That would be, let me just sort these. 6, 7, 8, 10, and 14. and then 3, swapping as I go, 4, 11, 5, and 9. This would be 9, 11, and 13. So now notice I have 2 separate sorted arrays, and it took me 56 comparisons to get here using a selection sort. Now 56 is a lot less than 120, but now I have to merge these. Well, how will I merge these? What I will do is I'm going to create a temporary array, a separate array of size 16 as well. So this is size 16 as well. And I'm going to compare, I don't need to look for the smallest value in the whole array. I only need to compare the 2 values at the start of these. And I'm going to take the smaller one, I'm going to copy it to my temporary array, and then I'm going to ignore it. I'm going to now no longer compare 2 to 1, I'm going to compare 2 to 3. 2 is less than 3, so I copy 2 down, and I stop considering 2. Now I'm comparing 3 to 6. 3, smaller than 6. Takes me to 4. 4, smaller than 6. Then I compare 5. 5 is smaller than 6. Then 9 to 6. 6 is smaller than 9. 7 is smaller than 9. 8 is smaller than 9. 9 is smaller than 10. 10 is smaller than 11. 11 is smaller than 14. 13 is smaller than 14. 14 is smaller than 16. 16 is smaller than 20. 19 is smaller than 20. And then finally, I only have this last value, 20, left over. Here we go. And then all I need to do is just copy this back up to the old array. So the number of comparisons that I do is however many x's I have, because every time I compared 2 numbers, I x'd out a number that was smaller. And I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 x's. And in fact, because I'm ultimately comparing up to at most 15 pairs of numbers, what I'm going to say is, in a worst case, and this is a worst case, in a worst case, this merge process takes 15 comparisons. In a worst case. So 15 comparisons, plus the 56 I've already done, that is 1, carry the 1, 71. Well, look at this. When I did a selection sort, I needed 120 comparisons. But when I simply broke the problem in half, sorted each side independently, and then merged, well, look, that was faster. Just by breaking it in half one time. So, not breaking it in half was 120. Breaking it in half one time was 71. Let's see what breaking it in half twice does. Let's try that. So again, same array of 16. Okay, same array of 16, but now I'm going to break it, hang on, 1, 2, 3, 4, 5, 6, 7, 8. I'm going to break it in half, and then I'm going to break it in half again. So you can think of this as now I'm sorting 4 arrays of size 4 rather than 2 arrays of size 8. Well, how many steps does it take to do a selection sort on an array of size 4? Well, it would take at most 3 comparisons plus 2 plus 1, or 6. But I can't do that one time, I have to do that 4 times. So 6 plus 6 plus 6 plus 6, all of these together, 24. But now I need to do the merge. This merge, merging the 2 left ones, is going to take at most 7 in a worst case comparisons. And this is going to take at most 7 to do this merge. Then that is going to give me 2 arrays of size 8, so these would be whole again and sorted, and then I have to merge those, and for the same reason as before, that merge takes 15 steps. So I have 24 from the sorting. I have 2 times 7 for the first merge, or 14. So 24 plus 14, and then 15 for the final merge. Let's add those numbers up. This is 8 plus 5 is 3. Carry the 1. That is 53. Well, look at that. This is even smaller. Let's go one step further. Let's go one step further. Now I break this down to size 2. So I have 8 arrays of size 2. Now, if I have an array of size 2, how many comparisons do I need to do? How many comparisons would I need to do to sort this array of size 2? Only one, right? I need to compare the first number to the second number to determine the correct order. So I have one comparison. And I have one comparison 8 times. So I have to do 8 comparisons once. Then I perform the merge. How many steps will it take to merge these two? Because what I'm going to do is I'm going to merge these two together, and then these two together, and then these two together, and then these two. So how many steps will each merge take? Not one. It will take more than one step. In a worst case, this will take 3. I'll have to do 3 comparisons. So I have 4 of those. So that's 8 times 1 for the sorting comparisons. Then for the first merge, 3 steps times 4. And we've already worked out this one. This is at most 7 steps times 2. 7 times 2. And then merging the last step is 15 times 1. So that is 8, 12, 14, and 15. Let's add those up. That's 20, 34, 49. And look at that. It's even less than that number. This fact that we can make the selection sort faster just by breaking in half and merging is what motivated the merge sort. And the merge sort is taking a large array and breaking into smaller arrays, sorting those, and then reforming them. And the merge sort can be implemented in code rather simply. Here is the code for the merge sort. That's it. Now there's a caveat here, we'll get to that, but the merge sort, we're going to take in a given array. We have this helper temporary array. That is, remember how I talked about I'm copying the values down to a temporary array and then copying them back up when I was doing the merge? That's what that's for. You don't need to worry too much about exactly how it works. Just be familiar with, there is a second array that's used as kind of scratch work. And then we're going to define a left and a right. And initially left, I'm going to sort from 0, the first element of the array, up to a.length minus 1, the last element of the array. I then find the center, and I sort the left half, and then I sort the right half, and then I merge the two halves. And that's all I need to do. Now, the merge code, that gets kind of crazy, and you can look through it and figure it out. The merge code works exactly how I illustrated the merge on the whiteboard. So you can go back and look at it and try to trace through this code and figure out how that exactly works. But this is the basic idea of the merge sort. The merge is only combining 2 sorted arrays into one. So now, let's illustrate that. Let's go over to the whiteboard. And I'm going to want 8 numbers between 1 and 100. Please try to get them in some kind of random looking order. And then I will illustrate a merge sort. So give me some numbers here while I get set up. Okay. 78, 40, 23. 93, 36, 77. And 29 and 8. So here is how the merge sort works. I am not sorting this array. I'm going to instead sort the left half first. So here's how I sort the left half. First, I identify that the left half is 78, 40, 23, and 93. Now I need to sort this, but how am I going to sort it? Well, I'm going to sort it with a merge sort. So I'm going to sort the left half first, 78 and 40. And now this is where it gets a bit weird because you think, okay, we stop here, right? No. We need to do one more split. I'm going to split and sort the left half first. So I'm sorting the left half of this array. All right, ready? I'm going to sort it. And I'm done. The left half is now sorted. Because there's only one element. One element is always sorted. It can't be out of order. Then from there, now that I'm done sorting the left half, I recurse back up, and then I sort the right half. And once again, I am done. Now that I have sorted both of these halves, I'm going to merge them. And I merge them by saying I'm going to use a temporary array to help me. That's where the temporary array comes in. It's down here, and it's just, again, think of it like Scratch workspace. So I'm trying to put into index, let's keep in mind the indices, 1, 2, 3, 4, 5, 6, 7. So this is index 0 to 3. So this is index 0 and 1. This is index 0. This is index 1. So then in my temporary array, I'm going to take which of these two is smaller? 40. I have used 40, so now I'm not going to consider it. Therefore, there's no other number to use, so I'm going to have to put 78 and 1. And then I copy back into my array, which remember, my array is up here. There aren't actually new arrays here. This is all the same array. I copy back into my array 40 and 78. And as a result of that, everywhere where it's 0 and 1, 0 is now 40, and 1 is now 78. I won't illustrate this every time, but just understand that this changes the array at all levels, because this top half is only one array. So 40 and 78. So that's what happens after the first merge. So I could illustrate it that way the whole way through, but instead I'm going to illustrate it in a way that isn't precisely correct, but is at least more useful for the sake of seeing what happens. So going back to 78 and 40, 78 and 40, and 78 and 40. Now, when I split these up, again, this is what I showed a second ago was more precisely how the code works. This is how to visualize it. And the two actually do conflict, but that's okay. So I need to merge 40 and 70 into an array of size 2. That gives me 40 and 78. Now, I need to sort the right half. 23, 93, which means it's 23 and 93. I merge these two. 23 is smaller, it goes first, then 93. Now I need to merge these two halves. That merges into 40, that merges into 23 is smaller than 40, so 23 first. Then 40 is smaller than 93. 78 is smaller than 93. And then 93. Now, we come back up. This half is sorted. We sort the right half the same way. So we break it up, 36, 77, 29, 8. We break this in half, 36, 77, 29, and 8. So 33 and 77. 29 and 8. We then merge. And these actually merge in order, 33 and 77. And same with the right half. Actually, we switch the order here. It becomes 8 and 29. We now need to merge these two. 8 is smaller than 33. 29 is smaller than 33. And now, since there's nothing left on the right side, we just copy the left side over one at a time. 33, and then 77. Now we merge these two halves into an array of size 8. 8 is smaller than 23. 23 is smaller than 29. 29 is smaller than 40. 33 is smaller than 40. 40 is smaller than 77. 77 is smaller than 78. And now all that's left to copy over 78 and 93. That is how you perform the merge sort. That is the illustration of it. Are there any questions about how it works? Any questions about how we would do it by hand, as I just did? So now, why is merge sort so much faster? Here's why. Let's count the number of comparisons I would have to do in a merge sort in the worst case. How many comparisons do I do? Now, technically, above this line, I don't do any comparisons. These are just recursive calls. I don't count them, so I'm not going to worry about them for now. How many comparisons do I need to do at this layer? Well, I need to compare these numbers, so that's 1. I need to compare these two numbers, that's 1. These two numbers, that's 1. And these two numbers, that's 1. That means I have 4 comparisons here, which I'm going to note is less than 8, where 8 is the size of my array. So this is less than 8. Now, how many merges do I need to do at this level? How many comparisons? Well, between these two, as we talked about before, I need at most 3, and at most 3. 3 plus 3 is 6, which I'll note again is less than 8. Finally, the merges at this last level. At most, we have to do 7, for the same reason we talked about before. 7 is less than 8. How many rows do we have? The number of rows that we have is log base 2 of n, because that's how many times that we can split this array in half. What's the upper bound for the most comparisons that we would need to do at any level? We would always need to do less than n. So n times n log n. That's the number of comparisons that we need to do. This is why merge sort is O of n times log base 2 of n. And it's why it's so much faster. Remember, I ran that selection sort yesterday. Started at the very beginning of class. It never finished and I gave up on it. It would not be finished today if it were still running. Merge sort like that. That's because this is not a little bit better than n squared. This is way better than n squared. Now, some of you may be thinking, okay, that illustration may have been helpful, but I don't know, I still maybe am not getting it. And I understand that. It's a lot to take in. It's a lot to take in. We also have more illustrations in the slides, I just want to note. So you can see that same illustration occur here. But some of you, this may not be your cup of tea. You may need some other thing. I'm sure there is one of you sitting out there right now saying, you know what, Professor McBurney? What would really help me understand how a merge sort works is if you could show me an illustration in the form of traditional Central European folk dance. And to that person I say, I have good news. Because there is a group called the Algorithmics. The Algorithmics. Oops. And the Algorithmics do just that. Here is the merge sort in the style of a Transylvanian Saxon German folk dance. And I'm going to let the sound play so you can hear it. Sorry, you couldn't hear me. So I was just calling along what was happening, but you could see it. So now we're merging A2 with A3 and A4. A2 is smaller than A4, so A4 comes down. So this stage front, that's the temporary array I was talking about. Sorry, I thought I had unmuted my mic, but apparently I had not. And now they step back. Now we need to merge A0 through A1 and A2 through A4. So we compare A0 to A2. A2 is smaller, so it goes first. A0 to A3. A0 goes first. Now A1 to A3. A1 goes first. And since there's nothing left to compare to, A3 and then A4 move down. And now we've done with that merge, we copy it back up to the original array. And then we repeat the process for the right side. And for the sake of time, and also because it's funny, if you didn't know on YouTube, you can change the playback speed. And this is speed 2. Now we split. A7's by itself, nothing to merge. A8 and A9 split, now they merge. Now we merge A7 with A8 through 9. Now we merge A5 and 6 with A7 through 9. And now, we need to merge the left and the right half, and the flourish. So, this is a YouTube channel called the Algorithmics, and if you ever get lost on a sorting technique, they illustrate them with European folk dance. And I will link their channel here in chat. You can see it there, so you can just Google it. That is also their channel. And they have heap sort, they have quick sort, they have binary and linear search, in case you're still lost on those. Select sort, bubble sort, insertion sort. Now, what is cool is to see the sorting techniques visualized. And so, there's tons of visualizations out there. Sorting visualizations. And it has cool noises. Also, you can tell I like Yella's Marble League, so that's fun. also video game speedrunning. But this is the quick sort. We haven't gone over that in class. It's probabilistic. But that's a visualization for quick sort. Here's merge sort. And I'm going to slow this one down. Sorry, here's selection sort. Notice we're repeatedly selecting the minimum, moving it to the front. And then here's the merge sort. You can kind of see, like, there's a merge, there's a merge. It also sounds cool, which is fun. And it also makes fun noises, so... The other one, though, is you can see them all race against each other. So here are sorting algorithms racing. And what I'm going to do is I'm going to quickly point out, so starting with a random order. Selection sort is up here. Insertion sort is top right. Merge sort is here. Bubble sort is here. The other sorts we haven't gone over. So these three are the three we have most gone over. Selection, insertion, and merge. And you can just see how much faster merge is than the other two. Notice that it's done, and the other sorts are still taking a lot of time. Fun fact, it's also fun to go on YouTube and watch Neil deGrasse Tyson videos at half speed because he sounds high. And that's funny to me because I'm 14. Anyway. So that is the merge sort, and I hope it's clear why we call this strategy divide and conquer. We break the problem up into smaller, individual bite-sized problems, and then merge them back into the whole. Are there any questions? Are there any questions about any material we've gone over today? Now, divide and conquer is a paradigm of problem solving. It can be used in other problems, and it often is used in other problems. Divide and conquer, generally the goal is to take something that is either n runtime and shorten it to log n, or n squared and shorten it to n log n, or n cubed and shorten it to n squared log n. The idea is you can take one of those exponents and turn them into a log n. That's often the goal of divide and conquer. And when we can apply it successfully, we get that benefit. So with that, that is why collections.sort in Java uses merge sort. So the easiest way to do a merge sort, just use collections.sort. And that uses a merge sort because it's so much faster. You can't, by the way, there's no way to change the sorting technique of collections.sort. It will always do merge sort. You can't make it do selection or insertion or anything like that. With that, that's actually all I have today. If people have questions, I'll happily answer them. But otherwise, I'm not going to present any new material today. I just wanted to explain how recursion, first, how to do recursion, because that's an important skill to learn. But then second, how recursion can be used to improve problems that we've already solved, like sorting. Doesn't always improve. Sometimes it doesn't. And again, anything you can do with recursion, you can do with loops. But the idea of recursion helps unveil some interesting solutions. And also, sometimes it's really hard. Like, I don't know how to write a merge sort without recursion. I don't know how to do it. It sounds like a pain in the ass. I don't really want to do it. Anyway. Alright, so if there are no questions, I will end it early today. And I will see everyone tomorrow. Tomorrow will be a class we talk about concurrency. And the idea of concurrency is the idea that your computer or your program can do multiple things at once. So our computer is basically hopeless for calculating a Fibonacci sequence above 50 recursively. I mean, if you did threading, you could probably do it. What's my favorite sort? The merge sort. I think there's a certain beauty or symmetry to it. Quick sort, probabilistically, is the fastest, but it's that gets into something I'm just not ready to talk about. You're right, there is a closed formula for Fibonacci, and that formula is, I believe it's 1 plus root 5 over 2 to the power of n plus 1 minus root 5 over 2 to the power of n, if I remember correctly. And 1 plus root 5 over 2 is phi. Yeah, it's a fun formula. It's a fun formula. It's fun to work it out, I think. I have a weird definition of fun. I enjoyed math. I love discrete math when I took it. I love math. I coincidentally didn't have a girlfriend until my 20s, so, you know, maybe the two are connected. I don't know. Anyway. I'm not familiar with math counts. I did skip senior prom to go to state math science bowl. Actually, no, national math science bowl, because we won state. Yeah, I did skip senior prom to go to national math science bowl. That is actually a true story. I have the t-shirt and the frisbee to prove it. All right, thank you all. I'll see you all tomorrow with concurrency. Um, Tomorrow is going to be a harder lecture, but if you can follow along with the lecture, and again, you can always rewatch it. If you follow along with the lecture tomorrow and more or less do what I do, then you will find homework 5 just an or homework 4, excuse me, just an application of what I do. So tomorrow's going to be a rare class because I'm going to do the daily activity in class. I'm going to walk you through the solution because that solution is going to come up on homework 4. So we're going to do that one together. I will see everyone then. Take care.